Greetings, I am Nandini Tewari, today demonstrating the third problem proposed by the 27th IYPT. The construction of a rigid ramp walker with four legs walking down a rough ramp and investigating how the geometry of the walker and relevant parameters affect its terminal velocity of walking. So here I have constructed two different rigid ramp walkers with two different purposes. Both of them have four legs as specified in the question. So here is the first rigid ramp walker. I have made both of them with A4 thick sheets. You can use any type of thick paper, even cardboard. Now, for the first ramp walker, the main body of this ramp walker is of the dimensions 4 into 4.5 inches, while each leg is of the dimensions 2.5 into 1.5 inches. The second ramp walker is my personal take on using these rigid ramp walkers for a practical purpose to improve the world in some way, to which I will come back in a while. Ramp walking toys have actually been around for quite a while. The first ones were metal elephants produced back in the 1800s. In the 1930s and 1940s, the popular material was plastic that was made into Disney and other popular characters. Recently, there has been a surge in wooden ramp walking toys. Now, before we start with the technicalities, let us see how this ramp walker works. So like we just saw, the ramp walker moved along the ramp very swiftly. Here, the surface of the slope that I am using is cardboard. I have tilted the cardboard here at an angle of approximately 15 degrees in order to form a slope for the ramp walker to walk on. Regardless of which material you end up using to form your slope, please ensure that your surface has a certain amount of roughness to it to enable the frictional force to drive the movement of the ramp walker. Now, a few observations regarding the ramp walker include: the two front legs are the ones which are actually walking. As one lifts up, the other goes down. The two back legs, on the other hand, are mainly present for support, as they create balance at the back by being dragged throughout the trip. If in case your ramp walker's legs are too weak, adding a piece of paper like I have at the hinging point of the legs prevents the ramp walker from falling. As you can see here, I have added pieces of small paper to each of the legs to prevent them from falling. In case the ramp walker simply slides down the slope instead of walking, adding more weight to the structure might help. You can start by adding some weight to the center of the body and decreasing and increasing the weight as required. Now let's come to the physics behind the ramp walker. It is essentially a mechanical toy that works by friction and gravity. Let us now see the formula. So like we just saw, the formula for the terminal velocity here is root 2 mg sine theta upon density into area into coefficient of friction. The values for each of them, as also listed on the screen, were: since 2 is a constant, the value remains the same. The mass of the ramp walker is 0.002 kgs. The acceleration due to gravity here is 9.8 meter by second square. Theta, as mentioned earlier, is approximately 15 degrees, so the value of sine 15 is 0.2588. The density of the cardboard is 689 kg per meter cube. Area of cardboard is 0.835 meter square, and finally, the coefficient of friction is 0.3. After plugging in these values into the formula, the final terminal velocity of the ramp walker is 0.013157 meter by second. Hence, as observed, the mass, the acceleration due to gravity, and the value of theta directly affect the velocity of the ramp walker, whereas the coefficient of friction, the area of the cardboard, and the density of the cardboard affect it inversely. Now I shall talk a bit about the ramp walker model that I worked on in trying to modify the usual model into becoming something which can be used in practical day life. So as you can see, this is the model that I worked on. It looks pretty similar to the original model that we saw in the video as well. But this one has a loop going from beneath. This loop here is essentially there to help those who cannot come down a ramp easily, those with a disability or those using a walking stick or a wheelchair. So the problem here is to solve that those people who cannot come down the ramp are supposed to usually take somebody else's help or come down with great difficulty, often at the risk of falling down. This ramp walker model, on the other hand, helps them sit down on this area here, and the ramp walker, as we saw on the screen, can just walk down on its own. Here, we make them independent and we don't have them rely on somebody else to carry them up and down the ramp. Again, this is a very basic model. There is really no mechanism that I have worked on for this ramp walker to walk back up the ramp. This is essentially for it to come down. I worked only on the coming down model for now. Since coming down is much riskier than going up, people are always often at risk of falling down while coming down the ramp. Hence this model. The mass will be adjusted accordingly, and the working of the ramp walker will be adjusted accordingly, since each person will have a different amount of weight that they add to the ramp walker. Hence it will be affecting the speed of the ramp walker and its movement as a whole. So that those are very technical points which we will have to look into, but this is just an idea which I have worked on and will continue to develop as time goes on.